So, good afternoon. Dr. Majid, can you hear me?
Yes, sir. We can hear you, but participants are not there. Just we can wait for another 2 to 3 minutes,
Okay,
so the
fine.
participants can join.
ये तो वो है सुभाष अब चले गए। बोल रखा है कि 3:30 से स्टार्ट होगा, 3:33 बजे तक कोई नहीं आया। पता नहीं सर। अभी दानिश सर का है, फिर आपका है। 20 मिनट का है, मतलब 3:10 पे आपका खत्म होगा। पहले स्टार्ट
हाँ,
Yeah.
Yeah. Good afternoon. Welcome to our next session of this event. I think we are starting with contributory talk first. This will be given by Dr. Mohammad Danish Siddiqui. He is currently working as assistant professor in Department of Mathematics, College of Science, Zezan University, Saudi Arabia. Okay, so Dr. Danish. Please.
Good afternoon, everyone. Should I start? Shall I
Yeah,
start?
yeah.
Okay, thank you very much. Good afternoon to everyone. This is the file is available.
Yeah.
Okay. So once again, thanks for Dr. Majid and his team to inviting me for this talk. So the title of my presentation is the relativistic space-time with magnetic energy momentum tensor. So I have picked this energy momentum tensor and study with the Einstein gravitational equation. And first of all, this talk is dedicated to Indian First Education Minister Maulana Abul Kalam Azad. So the general relativity is the best way to study the large scale structure about the universe theoretically. So it is observed that the general relativity without taking into account the dark energy cannot be described the acceleration of early and the late universe or expansion of universe. So to explain the cosmological dynamics, and the standard approach is given by the modification and Einstein gravitational field equation, which introduced by Einstein in around 1920. So Einstein field equation provide the best fit to observe the data with the further assumption and an hypothetical component of universe known as dark matter. So basically, this universe is a combination of dark energy and dark matter. And we are working in 4-dimensional Lorentzian manifold. So because time is the 4th dimension, so that is why we say this is space-time manifold, and gravity is the curvature of this space-time. And the movement of gravity can be explained as a wave function. So this is the main equation for my talk. Basically, this is the Einstein equation, and these are the components of Einstein gravitational field equation or Einstein field equations, where this RA, this is the Ricci curvature, and where R is the scalar curvature, and G is our metric about this Riemann metric for this space, and E is the energy momentum tensor or stress energy momentum tensor. So here this sorry.
Yeah, Dr. Danish, you may continue.
Okay.
Please.
So here on the left hand side, this component is energy momentum tensor T of AB, and the +1 is the cosmological constant. So this equation is Einstein equation, and here the energy momentum tensor play an important role. So this energy momentum tensor basically, for various type of space times, we have different energy momentum tensor. So in this paper for this study, I have considered a different type of energy momentum tensor and try to study some property about curvatures and some other things. So basically, idea about this general theory of relativity proposed by Einstein in around 1920. So during the last 100 years, it has been one of the most active research area in both in physics and mathematics. So beside this theoretical study, general relativity also have gained some great success in engineering and applying in our daily life. So it's have a lot of applications. The most obvious solution is the Minkowski space-time, which is a 4-dimensional Euclidean space with Lorentzian matrix. So both space-time of general relativity and cosmology is used to model connected 4-dimensional Lorentzian manifold. So this is the best model to choose to study the space-time Lorentzian manifold, where the Lorentzian matrix having the signature with --++. So that is the essential in general relativity. So this is the best model to study the space-time manifold. And in addition, the Lorentzian manifold geometry is started to analyze the nature of vectors at the manifold. So as a result, the Lorentzian manifold become the best tools to analyze the general relativity. So for finding the Einstein solution, the general solution for Einstein field equation, Lorentzian manifold is said to be perfect fluid space-time if the Ricci tensor take the form. So Ricci of UV is equal to A, where G is the metric and B is eta of U, eta of V. So this is the definition for perfect fluid space-time. If a Lorentzian manifold hold this condition, so we can say the space is perfect fluid space-time. So I want to extend just this space-time with the adding just generalize this thing. So using some extra conditions or some different type of energy momentum tensor and try to use with Einstein field equation and generalize this space-time. So in this equation where A and B are scalars and eta is a one form, metrically equivalent to the unit time-like vector fields because it is a space-time. So Lorentzian manifold considering the time-like vector field. Now the energy momentum tensor. Energy momentum tensor play a major roles for content of space-time. Matter is assumed to field having density, pressure, and having dynamical and kinetic quantities like velocity, acceleration, shear, and expansion. So the matter of content is very important as far as the space-time study is concerned. So now here, a perfect fluid is a standard cosmological model. A perfect fluid also has no heat, conduction, and no viscosity. Now in this study, so this is the main difference here in my paper. I have assumed the space-time filled with the magnetic energy momentum tensor. So this is the different thing is here. As a matter of content, having magnetism, magnetic fluid density, magnetic flux, and pressure is said to be magnetic fluid space-time or magnetofluid space-time. So that is why this space is named to be magnetofluid space-time due to the content of this space energy momentum tensor, magnetotype. So for further investigation, we need some definition. So a semi-Riemann manifold of dimension length greater than 3 is said to be generalized quasi-Einstein manifold if its Ricci tensor does not vanish identically and satisfy the equation 2.1. So this is the condition for Einstein manifold when a space-time manifold is a quasi-Einstein manifold space-time or quasi-Einstein space-time manifold. By equation number 2.1. So here there are two generators of these things. One is eta and other one is gamma, where B is not equal to 0, C is not equal to 0. Eta and gamma are no one form. And one is space-like vector field. Xi is a space-like, the unit vector xi and xi is zeta are one form, and they are orthogonal to each other. Also, xi and zeta are the generators of this manifold. So if C is 0, then M reduce a quasi-Einstein manifold, which will be then it will reduce to perfect fluid space-time. So this C, if C is not equal to 0, so then this space-time will be generalized quasi-Einstein manifold. And when C is 0, so M will be the quasi-Einstein space-time manifold. So this is the extra condition, the extra term for this. The C will be, and so throughout this paper, C will not equal to 0. Now in magnetofluid space-time, the energy momentum tensor T is of the following form. So this equation 2.2 is very important. It is, I'm trying to express this equation in global coordinates. So this is the expression for energy momentum tensor for with having magnetic flux, magnetic permeability, other things are there, pressure and density also available in this expression 2.2. So here rho is defined the magnetic fluid density, P indicate the pressure, mu is magnetic permeability, which is very important for magnetic field, and gamma is the magnetic flux, and capital H, which is denote the strength of magnetic field, such that we have this condition eta of u is equal to this is the condition for time-like vector field or space-like vector fields, where z of xi is -1 because this field is V is a space-like magnetic vector field, and xi is time-like, where zeta is time-like and xi is unit time-like vector field, and another one is space-like magnetic flux vector field zeta, where g of zeta is equal to 1. So therefore they are orthogonal to each other and generate the magnetic fluid space-time. Now this is equation number 2.3. Already I have mentioned this is Einstein gravitational equation with cosmological constant lambda 2.3. So here in equation 2.3, I have used the equation of energy momentum tensor for magnetofield or magnetic type energy momentum tensor, and let's see these results. So when I have used this equation 2.2 and 2.3, we obtain the Einstein field equation for a magnetofluid space-time, which is represented by in 2.4. So with the help of equation 2.2 and 2.3, we turned up 2.4. So from here you can see this Ricci curvature expression is here, and this is an analogous expression like generalized quasi-Einstein manifold, where these three coefficients of G, eta and gamma. So here a relativistic magnetofluid space-time considering the magnetic flux satisfying the Einstein field equation. So we have following theorems. Theorem 2.2, a relativistic magnetofluid space-time obey the Einstein field equation with cosmological constant, magnetofluid density and pressure is a generalized quasi-Einstein space-time. Also, after contracting equation 2.4, we will get the value of scalar curvature. And so, because scalar curvature is constant here, so a relativistic magnetofluid space-time, we have an interesting corollary, a relativistic magnetofluid space-time obeying the Einstein field equation with constant scalar is an imperfect fluid space-time. So this is because this is different from perfect fluid space-time, this equation. So clearly it is just like a viscous fluid space-time or imperfect, more generalized form, imperfect fluid space-time equation. So now the next section is curvature characteristic on space-time manifold in GR. So these two pictures can provide some idea about how a curvature will work around a space-time. So curvature at any point in any surface. So curvature moving from point to point on any surface, and curvature just you can assume some curvature around a space-time manifold. Now, since we have two generators of this equation tensor, xi and eta, and they are orthogonal to each other. So from 2.4, we will get equation 2.7. So Ricci equation when u and xi and u is eta. So curvature characteristics are here. So in 5, this is the definition about the famous Godazzi tensors. So if a non-vanishing Ricci tensor of semi-Riemann manifold satisfy the condition 2.8, where the derivative of Ricci curvature with respect to another vector field u is called Godazzi type. And also, if a Ricci tensor I of a semi-Riemann manifold satisfies the condition 2.9, then the Ricci tensor is said to be cyclic parallel. So these are these two famous characteristics of curvature if you have an expression of Ricci curvature tensor. So after I have skipping the calculation, so these are the main results here regarding to this definition. In a relativistic magnetofluid space-time, obeying the Einstein field equation with constant associated scalars, if the Ricci tensor is of Godazzi type, then the associated one forms eta and gamma, they are closed. Another theorem 2.8, in a relativistic magnetofluid space-time, obeying the Einstein field equation with the constant associated scalar, if the generators are killing generators, where our generators xi and zeta, if they are killing vector field, then the Ricci tensor of magnetofluid space-time is cyclic parallel. Another results related to our previous one, if in a relativistic magnetofluid space-time with closed one form eta and gamma, then the energy momentum tensor of magnetofluid space-time is Godazzi type, if and only if Ricci tensor is Godazzi type. And same condition apply for the magnetofluid is cyclic parallel. Now I am next section is just about some specific curvature like conharmonic curvatures. This is a very famous curvature. So this curvature, I am trying to study curvature of conharmonic curvature on magnetofluid space-time. So a relativistic magnetofluid space-time is said to be conharmonically flat if the conharmonic curvature tensor L vanish, and it is defined by Ishii in this 10. So equation 3.1 is given, provide the definition of, provide the expression of conharmonic curvature tensor. So here this RIE, this is Riemannian, and now in equation 2.3.2, this is the Ricci curvature expression available. So from equation 2.4, you can easily calculate after some calculation, and using the definition of this generalized quasi-constant curvature is defined as, and using the property of both space-like and time-like vector fields xi and eta, we have this relation, this theorem 3.1. A conharmonic flat relativistic magnetofluid space-time obeying an Einstein field equation is an imperfect space-time of generalized quasi-constant curvature. So this is generalized form. Also, the next thing is the differentiation. If you will differentiate this previous equation, we find the divergence of this curvature. So we will find divergence of Ricci scalar curvature will be 0. So in view of 3.7 and 3.8, we have another result here, 3.2. In a relativistic magnetofluid space-time with associated form eta and gamma, the energy momentum tensor of magnetotype are not being recurrence one form, and this is therefore the magnetofluid space-time is conharmonically conservative because the divergence of this curvature is 0. So this is the conservation of curvature here. Same process for using another conformal curvature. So basically in this paper I have used two curvatures. So those who are interested, who can study other, because there are several curvatures, study with this space-time. So this is conformal curvature tensor, and represented by equation number 1 is given by equation 4.1. So if it will be vanished for in this space, so this space, it will be the last relation, a conformal. This is theorem 4.1. We'll get this result: a conformally flat relativistic magnetofluid space-time satisfying the Einstein equation of generalized quasi-constant curvature. Once again, considering the parallel condition with these two vector fields xi and eta, space-like and time-like, so we have find the value of Ricci curvature with respect to these vector field will be 0, and we get theorem 3.4.2. If time-like vector field xi and space-like magnetic field vector field xi are parallel, and space-like vector field and the time-like vector field both are parallel in this space, then the magnetic fluid space-time is Ricci recurrent. So this condition will be provided for Ricci recurrent. Now this section is very interesting. It's a very interesting section, because from this section, I'm trying to interpret some physical significance of this space. So if we consider the equation 2.4, and under this setting, if u and v are xi is time-like vector field, so find this equation 5.1 and 5.2. So we can say that this is the mu is equal to -1 upon pi, and the rest thing in the bracket will be considered as a constant. Why? So another way you can write capital H. This will be equal to -1 upon mu and p plus rho by 2. So the thing available in this bracket considered as a constant. So from here we will get another interesting result. In a magnetofluid space-time satisfying the Einstein field equation with cosmological constant, then the magnetic permeability mu and the strength of magnetic field H are given by 5.1 and 5.2. So after this calculation, we can find the value of magnetic permeability and the magnetic field strength. And consequently, from 5.1, this result 5.2 is a very physical result. Give the physical interpretation of this study. In a magnetofluid space-time obeying the Einstein field equation with cosmological constant, okay, then the magnetic permeability, and the magnetic permeability mu is inversely proportional to the strength of magnetic field. So this is the physical interpretation of this relation. So mu is inversely proportional to the magnetic field strength, capital H. Moreover, we can just rearrange this equation. Mu H is mu into capital H is equal to minus times the P plus rho by 2. So this is just provide a basic law of magnetization of physics, where B is a magnetic flux density, because this term on available on right hand side is just like B. This will be termed as a magnetic flux density. So mu, this equation 5.4 is nothing, just a very famous basic law of magnetization in physics. So now we turn up the following results. 5.3, a magnetic fluid space-time obeying Einstein field equation with cosmological constant, then the magnetic flux density, which is capital B, is proportional to the magnetic field strength if mu is constant. Now about the magnetic field intensity. So the magnetic field strength is also called magnetic field intensity. Magnetic field intensity is a quantity used to describe the magnetic phenomena in terms of magnetic field. So the strength of magnetic field at a point can be given in terms of magnetic field intensity. So now this fact will help with the equation 5.2. We turn up the following results in theorem 5.4. In a magnetic fluid space-time, for satisfied the Einstein field equation, the magnetic field intensity satisfied the Gauss law of magnetism, which is divergence of this H is equal to 0, because for just constant value. So divergence of H is equal to 0. So the Gauss law for magnetism is one of the four Maxwell equations, basically, which form the foundation of the entire theory of classical electrodynamics. Therefore, we also turn up the following results, theorem 5.4. So another physical interpretation of this conclusion: a magnetic field space-time obeying the Einstein field equation with magnetic field intensity H satisfied the Maxwell equation of magnetism, which is del H is equal to 0. Now we have a very interesting remark here. The theoretical implication of Gauss law for magnetism are staggering. Since the divergence of magnetic field is zero, we can express the magnetic field as a curl of another vector field, which we call the vector potential, such that the B is equal to curl of phi. If you consider B is a curl of some another vector field curl F, the magnetic vector field is very important. Many expressions are classical electrodynamics are similar, so we can express the as a vector potential. So this will lead the next final result of this paper. So from the 5.5 and using the above remark, in view of this equation and the above remark, we state the following theorem. In a magnetic fluid space-time satisfying the Einstein field equation with magnetic field H in form as a curl of vector field F, then the magnetic field is solenoidal. So these are some physical aspect or interpretation of this study. As far as we have considered, our energy momentum tensor is a magnetic type, having the magnetic flux intensity, magnetic susceptibility, and magnetic field intensity. These are some references, and at this point I have to mention that these some of these results are already published in Journal of Geometry and Physics in 2000 in the January 2021 with Professor Day. Some part of these results. These are the references. Thank you very much.
Thank you, Dr. Danis. You had a nice presentation. So any questions, comments? Please, Dr. Danis,
Yes.
is P in equation 5.1 and 5.2 momentum R is any other quantity? So can you explain on the comment in chat?
Which sir?
There's a comment in chat box.
Okay, let me check. Okay. Is P in equation 5.1 momentums are only the quantity? How the P is the pressure, and equation 5.1 and 5.2 momentums are any other quantity. R is scalar. Basically, I have used the scalar curvature R. So R is also in terms of because when we're contracting the equation of expression of Ricci curvature after using the energy momentum tensor. So when we contracting this value of R, so there will the P is also there. So when after some sort of calculation, you can find this type of expression. Those who are interested, I will provide the whole calculation because I have skip these lengthy calculation because these curvature expressions and other things are very contracting, are very lengthy. So I have just
correct.
So I will provide those who are interested. I will provide this.
In a conference or symposium, we have limited time.
Yeah.
Okay, so that's all. Okay, thank you. So thank you, Danis. So next speaker is Dr. Yeah.
Hello.
Yeah.
Hello. This is Professor Afsus Ali Sheikh.
Yes, sir.
Yeah, I have some comments and suggestions.
Correct.
To Danis.
Please, sir.
Welcome, sir.
Yeah. Danis, probably your theorem 2.2, you said this is a generalized quasi-Einstein.
Yes, sir. Because I have obtained the analogous relation that.
Yeah. And there are many other theorems, but
Yes.
My suggestion is the generalization of quasi-Einstein manifold. There are many kinds of generalization. Okay.
Yes, sir.
I have generalized quasi-Einstein manifold by Chakri, generalized quasi-Einstein by Day and Ghosh, generalized quasi-Einstein by myself as a pseudo quasi-Einstein. There are many kinds of generalization. So you should mention in that theorem that generalized quasi-Einstein probably, and that expression in the sense of Day and Ghosh probably, which you have obtained in this calculation, that generalized quasi-Einstein in the sense of Day and Ghosh. Okay, you should mention in the theorem. Otherwise, in the literature there are many kinds of generalization. People will confuse. Okay. Thank you.
Okay, sir. Thank you very much for your suggestion.
Good paper.
And currently, sir, I have to mention here at this point, there is one paper of yours I have also studied just before 2 months. There is a pseudo generalized, I think there is some D. It just look like imperfect GRW space time, like analogous relation like that.
Yes. If you decompose D, then it will be the both in Chakri case and then Ghosh case. But if not necessarily 0 to tensor can be decomposed. I have given some examples both in decomposition and non-decomposed case. That means whenever it is reducible, whenever it will not reducible. Okay.
Okay, sir.
That is a good example that is fitting. And recently I have given some of many examples of generalized Quasi-Einstein in the sense of Chaki, in the sense of Ghosh, and some other cases also in the various kinds of space times.
Actually, sir, I'm trying these tensors to infuse in some thermodynamical property of space-time.
Yeah. That I have seen some good results, but those results can also be some modified in some ways. So far, I have seen apparently. Okay.
Good. Thank you, sir, for your suggestion. Thank you, sir. I will surely follow these things.
Okay. Thank you, Danis.
Thank you, sir.
Our next speaker is Dr. Mobin Ahmed from Integral University, Lucknow. He has 18 years of national and international teaching and research experience. So, Dr. Mobin Ahmed, I request you to present your work. Please, Dr. Mobin. Dr. Mobin. Dr. Mobin, please unmute yourself. Okay, Dr. Mobin.
Salaam, sir.
Islam.
If I am correct, Dr. Danis, Dr. Mobin Ahmed Saab is your guy, was supervisor, correct?
Of course, he is my supervisor.
Yeah. Okay, sir, please. Mobin, sir, please.
Yes, sir. Good afternoon to all of you. First of all, I thanks the organizing committee of this symposium, and especially Dr. Mazid, who have invited me for this talk in the international symposium held in his department. The title of my talk is Differential Geometry of Solitons and Their Applications. As we know, there are different kinds of waves in our daily life, like water wave, sound wave, light wave, so many waves. So simplest form of the one-dimensional wave equation is del 2u by del t square equal to c square, del 2u by del x square equal to 0, and its general solution comes in the form uxt equal to some function of x minus ct. Also, the nonlinear wave equation, simplest equation is ut plus ux plus ux equal to 0. This is nonlinear due to the presence of u into ux. If you compare this equation with ut plus ux equal to 0, then c comes as 1 plus u. And then the general solution may be written like uxt equal to function of x minus 1 plus ut. Now, we define a particular wave that is known as the solitary waves. A solitary wave is a non-singular and localized wave which propagates without change of its properties like shape and velocity. The simplest form of solitary wave type solutions are uxt equal to sec hyperbolic x minus ct. Solitons are the solitary waves that maintain their shape and velocity under collision during propagation. The concept of the solitary wave was introduced by the budding science of hydrodynamics Scottish naval architect. His name was Scott Russell in 1834. The story behind this was John Scott Russell was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair of horses. When the boat suddenly stopped, not so the mass of water in the channel which had put in the motion, it accumulated round the prow of the vessel in a state of violent agitation. Then, suddenly leaving it behind, rolled forward with great velocity, assuming the form of large solitary elevation, a rounded, smooth, and well-defined heap of water, which continued its course along the channel, apparently without change of form of diminution of speed. This was the story in the month of August in 1834. And this beautiful phenomena Russell called wave of translation. And this phenomena attracted attention of scientists. Two Dutch physicists, Cartwright and De Vries, in 1898 presented their famous equation that is known as KdV equation for the evolution of long waves in a shallow one-dimensional water channel. His equation was ut plus 6 ux plus uxx equal to 0. That is del u by del t plus 6 u del u by del x plus del 3 u by del x cube equal to 0. In 1965, Jaguski and Kruskal solved the KdV equation by numerically as a model of nonlinear lattice and found that solitary wave solutions interacted elastically with each other. Due to this particle-like property, they term these solutions as solitons. There are some more equations which produce soliton, that is non-Sponder equation, that is NLSC, IUT plus alpha ux plus beta mod of u square u equal to 0, and another sine Gaussian as equation UTT plus UAX plus alpha sine u equal to 0, nonlinear reaction, diffusion, convection are NRDC equation UT plus V U M UX equal to D UXX plus alpha u minus beta UM. This equation actually the solution are the solitary waves or solitons. Now, solitons have many applications. Solitons pulses can be used as a digital information carrying bits in optical fibers. Solitary waves are very useful to study the fluid dynamics problems and in plasma studies also. The Josephson's junction solitons are used to study propagation of magnetic flux through the junction. Solitary waves arises in the study of nonlinear dynamics of DNA also. About 3 decades ago, Hamilton introduced the notion of Ricci flow and Yamabe flow. The Yamabe flow on a smooth Riemannian or semi-Riemannian manifold M can be defined as the evolution of Riemannian or semi-Riemannian metric by the equation del by del t of gt equal to minus rg, where rt is the scalar curvature of the matrix gt. In two-dimension, Yamabe flow is equivalent to Ricci flow, defined by del T GT equal to 2 SGT, whereas denotes the Ricci tensor for G. However, the dimension higher than 2, there is not such an equivalence, as the Yamabe flow preserves the conformal class of metric, but the Ricci flow does not in general. In more than 2 dimension, Yamabe flow preserves the conformal classes of metric, but Ricci flow does not in general. So they are different in more than 2 dimensions. The Ricci Sultan and Yamabe Sultan emerges as the limit of the solution of Ricci flow and Yamabe flow, respectively. These are the two equations here. Lead derivative of G along B plus 2s plus 2 lambda G equal to 0, and lead derivative of G along B equal to 2 R minus lambda G. Where the first equation is the Ricci flow equation and second is the Yamabe flow equation. Here, this dollar $B, that is the lead derivative of along B. And B is the called soliton vector on M. Lambda is a real number. In 2018, Deshmukh and Chen briefly study Yamabe solitons and find sufficient condition on the soliton vector field V so that the metric of the Yamabe soliton is of constant curvature. And Yamabe solitons have been studied by many researchers. Recently, in 2019, a new class of geometric flows called Ricci-Yamabe flow of the type alpha beta was introduced by Guller and Krasmarinu and is defined by this equation del by del T of GT equal to minus 2 alpha S GT plus beta R into G. After Guller and Krasmarinu, they introduced the notion of Ricci-Yamabe solitons. According to him, Ricci-Yamabe soliton of the type alpha beta is a Riemannian manifold which satisfies the following equation: lead derivative of G plus 2 alpha S plus 2 lambda minus B R into G equal to 0. Here alpha and beta are constants. Also, Ricci-Yamabe soliton of type alpha 0 is called alpha Ricci soliton, and 0 beta type, this is called beta Yamabe soliton. The notion steric Ricci tensor and Yamabe tensor was given in the study of Tachibana on almost Hermitian manifold and Hamada on real hypersurfaces of non-flat complex space form. Here, the steric Nita Ricci Yamabe soliton is said to be shrinking, steady, or expanding if it admits a soliton vector for which lambda is negative, 0, or positive, respectively. In particular, if mu equal to 0, then the notion of steric eta Ricci Yamabe soliton, which is given by equation number 3, reduces to the notion of steric Ricci Yamabe solitons. Recently, alpha co-symplectic manifold admitting steric conformal eta Ricci Yamabe solitons admitting quarter symmetric metric connection have been studied by John and et al. Now, here we define, this is the definition of the Lagrangian Parasasakian manifold. These equation number 1, number 4 and 5. If this is satisfied, then this is called Lagrangian almost paracontact structure. When it admits a Lagrangian metric G such that G of 5K, this equation number 6, for all vector field KL and the manifold with the structure this phi is I, eta, and G is called Lagrangian almost paracontact manifold. Almost Lagrangian paracontact manifold is called Lagrangian Parasasakian if this equation number 7 holds. Now, if M is projective curvature tensor S in an n-dimensional LP Sasakian manifold, then it is defined by this equation number 12, where R and S are the curvature tensor and Ricci tensor of the manifold, and Q is the Ricci operator defined by SU equal to G of QU E. An LP Sasakian manifold M is said to be normalized eta Einstein if its non-vanishing Ricci tensor S is of the form, this 13, equation number 13, where this psi1, psi2, and psi3 are smooth functions of on M. If Z3 equal to 0, respectively Z2 and Z3 equal to 0, then M is called eta Einstein, respectively Einstein manifold. A vector field V is said to be a affine conformal vector field if it satisfies this equation number 14, where rho is a smooth function
Dr.
of.
Mobin sir, sorry to interrupt you. Sir, we have a limited time, so please take care of time, sir. Please, sir.
Okay.
Okay, sir. Thank you, sir.
Now this theorem, see. If M and G, if Mg is an n-dimensional LP Sasakian manifold admitting spheric eta Ricci Yamabe soliton, then M is generalized eta Einstein manifold and scalars lambda mu are related by this relation lambda minus mu equal to dr upon 2. This is the first theorem, and based on this first theorem, there is a corollary. Let M be an n-dimensional LP Sasakian manifold. If M manifold admits steric Ricci Yamabe soliton with equal to 1, then M is an eta Einstein manifold. Moreover, the manifold is shrinking, steady, or expanding if beta is greater than 0, equal to 0, or less than 0. Now, theorem number 2. If Mg is an LP Sasakian manifold admitting steric eta Ricci Yamabe soliton such that the vector field V is an affine conformal vector field, then the manifold is generalized eta Einstein manifold and V is a affine vector field provided trace of phi equal to constant. Now, by next theorem, in a LP Sasakian manifold admitting steric eta Ricci Yamabe soliton such that the vector field V is the gradient of R defined by equation number 3, then either beta equal to -2 or V is point-wise collinear with the structure psi. Next theorem, if Mg is an n-dimensional M projectively flat LP Sasakian manifold admitting steric eta Ricci Yamabe soliton, then M is an eta Einstein manifold and the scalars lambda mu are related by lambda minus mu equal to dr upon 2. So, one more theorem on the M projectively flat LP Sasakian manifold admitting steric eta Ricci Yamabe soliton, then M is eta Einstein manifold, and the scalars lambda mu are related by lambda minus mu equal to PR upon 2. And here we have given an example of Ricci Yamabe soliton. We have taken 3-dimensional manifold and we define the independent, linearly independent here vector fields E1, E2, E3, and we calculated the metric of between these E1, E2, E3. And after some calculation, we calculate the curvature tensors, and with the help of this curvature tensor, we can find the this Ricci curvature tensor S also, and with the help of this, we find lambda minus mu equal to dr upon 2, which is the condition for the eta Ricci Yamabe soliton in the theorem. So in this way, this manifold which we have taken with the metric as Lorentzian metric, then this will represent steric eta Ricci Yamabe soliton. And these are the references. Thank you.
I have a question. Or is the chairman? Yeah.
Yeah, thank you, Mobin Ahmed sir, for your
Okay,
nice
sir.
presentation, sir. So, sir, there are some questions in chat.
Yeah.
Can you please answer first?
I can ask a question?
Yeah, you can ask. Yeah, please, sir.
First of all, thanks for Mubin Ahmed. Please, a nice talk. I have a question that you mentioned generalized eta Einstein, LP Sazakian. Can you give us an example? Because I know that even for LP Sazakian, there are a few examples. So because you put as an assumption that your LP Sazakian is an LP manifold is an generalized eta Einstein manifold. Please. And also you give an example for 3-dimension, which is not useful. And for LP Sazakian, generalized Einstein example. It would be very nice if we have an example. Yeah.
Sir, I have given one example, which is LP Sazakian manifold.
But it's 3-dimension, I think, and isn't it?
Yeah.
So is not good example for generalized eta Einstein LP Sazakian. So the assumption, be careful with the assumption that you have a generalized eta Einstein.
Sir.
ये हो गया ना बेटा क्या डल जाएगा इसके अंदर जगह है क्या इसमें किस करना पड़ेगा
This is the theorem which will give the generalized Einstein manifold, which has the relation lambda minus mu equal to beta.
No. The question is to give this is yeah, you put a condition, so this manifold is. Before that, so if you have an LP Sazaki with an generalized eta Einstein, if you can give us an example, it's okay, because otherwise it's the same question is for Yamabe foundation.
Generalized.
You gave us an example.
Manifold.
Yeah, it's difficult. I think maybe because can you show us an example, the last example, for example, just to check it again? Yeah, because I know that even LP Sazakian, there are a few examples. So for generalized eta Einstein, so it will be fantastic example.
Okay, there are some examples also, but in my here presentation, I have not taken all the part of this paper. So only something I have here presented. So I will not remember at this moment what was the example of this beta.
It's okay. So try to send us an email or something like that, because I know that for LP Sazakian there is there are a few examples. And you said there is, generalized eta Einstein, something, yeah, it's not so very simple, I think. But if it exists, it will be very, very nice. And more than that, the coefficients are functions, not even constant. Okay, thank you.
Sir, our student Tahir Manjur have some problems, questions. What will happen when lambda is less than, equal, or greater than in Rikiyama?
Lambda is
less than or greater than equal in Rikiyama.
then the Sultan will be shrinking, steady, or expanding.
And another question is, can we not use trigonometric function in place of hyperbolic functions in E1 and E2? Tahir Manju, are you there?
We not use trigonometric. We can use trigonometric functions also, but there will be a setting for that.
Okay. So thank you, Dr. Mobin Ahmed sir. Thank you very much.
Welcome.
Thank you, sir. So our next speaker is Dr. Ram Shankar Gupta. He is an assistant professor in School of Basic and Applied Sciences, Guru Gobind Singh Indraprastha University, Delhi. So, Dr. Ram Shankar Gupta, sir.
Yes, sir. Yes.
Okay, sir. You can present now, sir. Please,
Okay.
sir.
Thank you. Is it my slide is visible?
Yeah. It's visible.
Okay. Thank you.
You can put it in full screen mode.
Yeah, just I'm trying. Yeah.
And sir, please take care of time, sir.
Yeah. I understood.
Thank you, sir.
So, thanks to the organizer for inviting me to give a talk. My talk is on biharmonic hypersurface satisfying delta H equal to lambda H in pseudo-linear space. I will cover in this talk like hypersurface satisfying this condition delta H equal to lambda H. Then we impose a condition on the hypersurface that the hypersurface should have constant norm of second fundamental form. And then again we impose one more condition that it should have at most 6 distinct principal curvature. And using all these we'll prove 3 theorems and then also give an example. let EMS denote the m-dimensional pseudo-Euclidean space with pseudo-Euclidean metric G bar, where x1, xm are rectangular coordinates in EMS. Let x bar vector x denote the position vector of the isometric immersion from the hypersurface to the pseudo-Euclidean space. Then we say that this hypersurface having proper mean curvature vector field if delta h equal to lambda h is satisfied by this hypersurface, where delta is the Laplace operator, which is defined by G bar delta x y equal to delta of G bar x y, where y is del by del xi. So a generalization of this, like there was a theorem in Euclidean space for the hypersurface satisfying this condition delta h equal to lambda h, and similar to that in pseudo-Euclidean space also the same type of generalization given that the hypersurface satisfying 1.1, that is delta h equal to lambda h, is a biharmonic or is a of one type or a null two type hypersurface. Then Fernandez and Lucas studied these conditions for the hypersurface for the surfaces in Lagrange-Minkowski space E31, and they obtained that one of these surfaces is a surface of zero mean curvature. Later they showed that if the minimal polynomial of the shape operator of a hypersurface in Lagrange-Minkowski space is at most of degree 2, then it has constant mean curvature, and they also classified such type of hypersurface. Then Arunito et al. Proved that every non-degenerate hypersurface in 4-dimensional pseudo-Euclidean space with diagonal step operator satisfying delta h equal to lambda h has constant mean curvature. Although the shape operator of Riemann hypersurface is diagonalizable, but this is not true in case of pseudo-Euclidean or pseudo-Riemannian case. Further, they proved that they studied this type of hypersurface in E41 and E42, and they proved that this type of hypersurface has constant mean curvature. Then Liu and Yang in 2014 proved that every non-degenerate hypersurface in pseudo-Euclidean space with diagonal step operator satisfying delta h equal to lambda h and with having at most 3 distinct visual curvature has constant mean curvature. Further, they proved that every Lagrange hypersurface in pseudo-Euclidean space satisfying delta h equal to lambda h of non-diagonal shape operator with at most 3 distinct visual curvature has constant mean curvature. So now they classify, they have studied both the condition, like when the hypersurface having diagonal shape operator and when they have non-diagonal shape operator. For both, they obtain the result in case of 3 distinct principal curvature that this kind of hypersurface has constant mean curvature. Then we have studied this type of hypersurface with at most 4 distinct visual curvature having complex eigenvalue, and concluded that this type of hypersurface has constant mean curvature. Then further, Liu and Yang studied if hypersurface in pseudo-Euclidean space with at most 2 distinct curvature, and they obtained that it has constant mean curvature. Then we also then further we studied Lagrangian hypersurface in pseudo-Euclidean space satisfying condition delta h equal to lambda h under the additional assumption that the shape operator has at most 5 distinct eigenvalues, and out of that 2 of which are assumed to be complex has constant mean curvature. Further, we studied Lagrange hypersurface in 5-dimensional pseudo-Euclidean space with non-diagonal shape operators having characteristic equations like this, and we obtained that this type of fiber surface also has constant mean curvature. A submanifold of pseudo-Riemannian space satisfying 1.1 with lambda equal to 0 is called biharmonic. That is, each pseudo-Euclidean coordinate functions of M is a biharmonic, which is the condition is given by 1.2. So every minimal submanifold satisfying H equal to 0 are biharmonic. Now, Chain's conjecture in the Euclidean space is that every biharmonic hypersurface must be minimal in the Euclidean space. So Chain's conjecture is not true for submanifolds of semi-Euclidean spaces, but there are some results which confirm that the Chain's conjecture is true for hypersurfaces in pseudo-Euclidean space. Then Chain and Iskawa, they obtained some examples of proper biharmonic surfaces in 4-dimensional pseudo-Euclidean space, and they also proved that biharmonic surface in pseudo-Euclidean space, 3 space are minimal. Then Defever proved that biharmonic hypersurface with diagonalizable shape operator in pseudo-Euclidean 4-dimensional space are minimal. Then again, Andrees proved that biharmonic Larranger hypersurface in Minkowski 4 space are minimal. Then we proved that every biharmonic hypersurface with three distinct principal curvatures of diagonal shape operator in 5-dimensional pseudo-Euclidean space must be minimal. Again, we obtained that every biharmonic non-degenerate hypersurface of constant scalar curvature with diagonal shape operator in 5-dimensional pseudo-Euclidean space has 0 mean curvature, that is minimal. Every biharmonic Lagrange hypersurface in pseudo-Euclidean space with at most 3 distinct principal curvature of non-diagonal shape operator having minimal polynomial has to be minimal. Then it was conjectured that any hypersurface satisfying delta H equal to lambda H in pseudo-Euclidean space must have constant mean curvature. The related problem posed in the 1980s that classify null 2-type submanifold, because null 2-type submanifolds also satisfy this condition delta H equal to lambda H. In view of above, we studied hypersurface satisfying in the pseudo-Euclidean space satisfying delta H equal to lambda H, and in the result we proved, we assume that the hypersurface has diagonal shape operator with respect to a local orthonormal frame. We obtain this following result. Let M be a hypersurface satisfying delta H equal to lambda H in pseudo-Euclidean space whose second fundamental form has constant norm. Suppose that the shape operator is diagonalizable with at most 6 distinct principal curvature, then this type of hypersurface has constant mean curvature and constant scalar curvature. So from this theorem, we can obtain the result for biharmonic hypersurface also, and we obtain that the biharmonic hypersurface satisfying these conditions is minimal and also of constant scalar curvature. Then also we try to classify non-minimal hypersurface with extremal value of square of mean curvature, and we obtain this theorem 1.3, like let M be a hypersurface satisfying like H not equal to 0 and delta H equal to lambda H whose second fundamental form is constant norm. Suppose that the shape operator is diagonalizable with at most 6 distinct principal curvature, then lambda not equal to 0. Moreover, if lambda is greater than 0, then H is a space-like and H square less than or equal to lambda by n. Equality also holds if and only if hypersurface is isometric to a domain in pseudosphere having curvature lambda by n. If lambda less than 0, in that case, the mean curvature vector is time-like and H square is less than minus lambda by n, and the equality holds if and only if hypersurface is isometric to a domain in hyperbolic space, pseudo-hyperbolic space lambda by n. So what has been our approach? Approach is like this: using condition delta H equal to lambda H and the Fudagi covariant derivative of principal corrections in a simple form. You will see here lemma 1.4. Next, using lemma 1.4 and the Gauss equation, we express the derivative of connection forms with respect to an orthonormal frame in terms of connection form and principal curvatures, which is given in lemma 1.6. Further, we introduce some scalar functions to make computation simple, and using condition of constant norm of second fundamental form, we find some more lemmas 2.1, 2.2. Thereafter, using condition 6 distinct principal curvature on the hypersurface, we obtain some more vanishing connection form that you will see in lemma 3.2. Lemma 3.2 turns out to be crucial to achieve our result. We prove the main result that H must be constant by analyzing all the possible cases on non-vanishing connection form and using standard argument for the resultant of two polynomials. So these are the prelim I will skip because of time. You'll see this is the lemma. Here, this lemma expresses the covariant derivative of in case of hypersurface in pseudo-Euclidean space having diagonal shape operator. From above lemma, you will see that the vector field even is a geodesic vector field on M with integrable normal distribution, which is spanned by vector field E2 to En. In other words, B is tangent to a codimension non-Riemannian foliation of M. Moreover, linear operators, that is the shape operator A, and this nebula even commute because they are diagonal in the orthonormal frame, and the eigenvalue of nebula even are 0 and this minus epsilon 1 II. Like here you will see 0 or this one. Then we have lemma. Assuming this conditions of above lemma, we also have these conditions like equation 1.20, 1.20a to 1.20b. Then we have this lemma, like if you have a surface satisfying delta H equal to lambda H and having diagonal shape operator, and if second fundamental form is of constant norm, then we have these equations from 2.1a to 2.1g. Then we have lemma 2.2. Under the conditions of lemma 2.1, we also have following equations 2.3, 2.4. We'll see that derivative along EI of tau 01, tau 02, all are 0. Then we have this lemma, if hypersurface satisfying delta H equal to lambda H, such that mean curvature is non-constant and having at most 6 distinct principal curvature, then if second fundamental form is constant, then we also have equation 3.1 and 3.2. So now this lemma is very useful because here we are getting some more connections form to be 0, like this omega J1, JI1, JI2, JI2, or like 3.15. So if you use using all these conditions, we are able to prove theorem 1.1 by evaluating this computing the Gauss curvature. We get 4.1, 4.2, 4.3. So the question, natural question may be like why we have taken condition on the principal curvature or condition on the constant norm of second fundamental form. So the answer for that is a natural question may arise to examine exemption of theorem 1.1 for more than 6 distinct principal curvature. In this case, we need lemma 3.2 to be true, and one more expression is required in lemma 3.1 of this type. So if we differentiate it again, we are getting this value, and then we are getting 4.28. And if we apply this Lie bracket on this, we are getting this equation 4.29. and differentiating 4.28 in the direction of EI, we are getting EI tau 06 plus this 0, whereby we cannot obtain the equality like this EI tau 06 equal to 0 as it depends on this EI tau 14 also. So that was the reason we have to restrict ourselves on the 6 distributional curvature. Now I'll discuss example here. Consider the hypersurface in Lorentz-Minkowski space given by this 5.1. By direct computation, we find the vector fields E1, E2, E3, E4, and EI plus 1, and also EN. So EN equal to 1 by S, del T, form an orthonormal base of the tangent bundle of them such that E1, E2, E1 is a time line and the rest of the vector is space line. Then the unit normal vector field N is given by this. Further, we computed the covariant derivative of unit normal vector N, and we are getting 5.2. That is the diagonal fit operator at curvature. Now, if hypersurface satisfying delta is equal to lambda f, then we are getting that delta 1 equal to minus 2 by 2 here. And we are getting this equation 5.4. Further, if we given that m is constant, next equation 5.5. Solving this, we are getting 5.6.
Dr. Ram Shankar.
Yes.
Okay. Okay.
So similar to example 5.1, we can obtain the example of hypersurface MNR in En plus ENS like this 5.2. So these are the references. Thank you.
Thank you, Ram Shankar Gupta ji, for your nice talk.
Thank you.
And if someone have a precise question, please ask. So thank you, Ram Shankar Gupta ji, sir.
Thank you so much.
And next speaker is Dr. Alia Naz Siddiqui. She is currently working in mathematics market University, Ambala. So, Dr. Alia, please share your presentation, please.
Good afternoon, all of you. Am I audible?
Yeah, you are audible.
Okay. So just give me a minute.
Okay.
Is my screen visible to all? Is this visible?
No.
Not visible?
Not yet.
Now visible? Is this visible?
Not now.
Just give me 2 minutes, please.
Dr. Alia. आपने ज्वाइन करा? आपने ज्वाइन नहीं कर रखा क्या आपने? ये लैपटॉप कौन कौन? कौन? She's present. Dr. Alia?
Yes, yes. Am I audible?
Yeah, you're audible.
Yeah, let me share my screen.
आपका चेहरा दिख रहा था।
Is this visible?
Yeah, it's visible.
Okay, okay, okay. Thank you for waiting me.
Sure,
I'm so sorry. Yeah.
Sorry, Dr. Alia, for interruption.
Yes.
So please take care of time. So
Yeah, sure, sure, no problem. Okay. So good afternoon, all of you. This is a great opportunity for me to attend this event. So I'm from Department of Mathematics, Maharishi Markandeshwar Deemed to be University, which is located in Ambala, Haryana. Topic is a study of statistical submersions. These are the contents of my talk. Now, we will start with the topic Riemannian submersion, which is in the 60s, Gray and Neal gave the notion of Riemannian submersions, which is actually a tool to study the geometry of Riemannian manifold with an additional structures in terms of the fibers and the base space. And you can find many submersions in recent book, that is Riemannian submersions related topic. And you can find many applications in physics, for example, Kaluza-Klein theory, Yang-Mills theory, and etc. and so on. Watson was a great researcher who popularized the knowledge of Riemannian submersions under the name of almost Hermitian submersions, which is a complex version of submersion. And later on, B. Shahin gave such submersion for the contact matrix manifold, and it is named as contact Riemannian submersions. And you can find many good topics related to this submersions in his book Riemannian submersions, Riemannian maps in Hermitian geometry and their applications. Later on, Nielsen and Jubb discussed the Riemannian submersion from the viewpoint of statistics. And afterwards, Abe and Hasegawa, who were the main source for the notion of statistical submersions between the statistical manifolds. We can say that it is a generalization of some basic results of O'Neill given by O'Neill concerning Riemannian submersions and geodesics. For the contact part and the complex part, K. Takano found these terms that is called Sasaki-like statistical submersions and Kehler-like statistical submersions. And he used dual tensor fields. For complex part, he used J and J asterisk, and for the contact part, he used phi and phi asterisk. Later on, by Takano's studies, Vilku studied about almost quaternion structures and quaternionic Kehler-like statistical submersions and investigate some new properties of the submersion. Then Furuhata and Hasegawa, Okumaya and Sato studied the Kanmotsu statistical manifold as a work product of two statistical manifold. And with the help of this, we can study Kanmotsu-like statistical submersion. In recent article, Murathan and Shahin studied Kanmotsu-like statistical manifold and concentric-like statistical manifold. With the help of these manifolds, we have got new submersion, that is Kanmotsu-like statistical submersion and concentric-like statistical submersion, and which was studied by Atomur and Asgur. They studied about concentric-like statistical manifold and submersion. Similarly, in the recent article with Mohammad Dani Siddiqui and Atomur, we studied Kanmotsu-like statistical submersion, and we have discussed the properties of such submersion with conformal fibers also. In the continuation of study of different classes of statistical submersions, Vilku again gave a new concept of statistical manifold endowed with almost product structure called para-Keller-like statistical manifold and described its submersion as well. Again, he discussed some interesting properties with new examples. So we give some basic notations, we have taken M as a semi-Riemannian manifold and GM as a non-degenerate Riemannian matrix, and a torsion-free affine connection, Nebula bar, and combining, we can get a statistical manifold if your nabla bar is compatible to your metric. And it was given by S. Amari in his book. And the condition and the relation between the nebula bar and nebula bar asterisk, because since as we know that this is a generalization of Riemannian manifold, so we have two connections here. So we have the relation between two connections given in one, and we call it dual connections, or I can say conjugate, and should be torsion-free connections. Now I would like to tell the semi-Riemannian manifold, that is, if we have two semi-Riemannian manifolds, and one having index R and other having index S, and dimension of M is M and dimension of N is N, then I have a smooth and onto map omega, that's called omega, is semi-Riemannian submersion if we have three conditions that is given on the screen. And the pre-image of that point, that each point for which belongs to N is called fiber of M, and we have denoted it by M bar, and which is of course semi-Riemannian submanifold, and its dimension is M minus N, and M is total space and N is the base space. Some notations of vertical distribution, that is denoted by VM and HM respectively. Now, I would like to tell you about the statistical submersion. Again, we have two statistical manifolds, and a semi-Riemannian summation omega is said to be a statistical submersion if we have condition 2, which is hold for basic vectors x and y. And basic vectors are basically if we have x is a horizontal vector and x is omega related to a vector field x ray. And we have some tensors T and A, which are defined by O'Neill in his very famous paper, that is the fundamental equations of a submersion, and given by third and fourth. Basically, it will give you vertical part and horizontal part. Next, I can say that T and A, that is the tensors we have are skew symmetric operators on the tangent bundle of M and satisfying the equations 5th and 6th. Later on, by Takano, he gave T asterisk and A asterisk because of the statistical manifold that we have two tensors like phi and phi asterisk, J and J asterisk. So we have T asterisk and A asterisk. If A and A asterisk both are 0, then we can say that HM is integrable. HM means that here it is horizontal distribution. And A is with respect to nebula bar, and A asterisk is to nebula bar asterisk for the conjugate part. And we have two more relations which are given in 7 equation between T and T asterisk, A and A asterisk. Since we know that they are skew symmetric, so we have negative signs there. We have some useful properties that given by Takano in his very nice article, Statistical Manifolds with Almost Complex Structures and its Statistical Submersions, given by 2 lemmas, given below. Now, next we will discuss about the curvature tensor. That's like we have a Gauss equation in your Riemannian manifold theory, Riemannian manifold and submanifold theory. So we have the equation as in 13, which is very useful to find the inequalities or some relations, some properties on the curvature of your base manifold or base space, sorry, and the fiber. Next, we have mean curvature vector field, which is given in 16 equation. And next, very important part, that is submersion with isometric fibers if we have T0, and conformal fibers if we have the relation T is equal to 1/1 M minus N GM. And N is your tensor. Now, recently, in the first, with Danish Siddiqui and Al-Khaldi and Ali, we have discussed about the lower bounds on statistical submersion with the vertical Casorati curvatures, and we gave a very good example on statistical submersion. First of all, we discussed about the statistical manifold. Here we have proved that M is a statistical manifold of constant curvature with the scalar curvature -20. And in the continuation of this example, we have proved that omega is a statistical submersion by defining the a mapping between these two manifolds. And we have defined the horizontal distribution and vertical distributions. And it is easy to say that we have such relation. Now, I have already told you about the classes of statistical submersion. So I have again explained that Kehler-like statistical submersion was given by Takano, and quaternionic Kehler-like statistical submersion was given by Vilku and Vilku. Para-Kehler-like statistical submersion was given by G. Vilku. And Sasaki-like statistical submersion was given by Takano. Cosmetic-like statistical submersion was given by Atimur and Osgur. And in the recent article, we are discussing about Kenmotsu-like statistical submersion. The paper has prepared and we have submitted it as well. Now, I would like to give a glimpse of some important result on statistical submersion, and similar results have been proved for Kehler-like statistical submersion, Sasaki-like, and so on. See, we have almost 6 submersions right now with the on statistical part. So we can discuss various different submersions. We can obtain different submersions for statistical submersions. So these are the results given by Takano in his famous paper. Now, next topic is statistical solitons on statistical submersions. Ritchie flow equation was introduced by Ritchie Hamilton, who gave an evolution equation for matrix called Ritchie flow on Riemann manifold, which is given by 25 equation. And a solution to the Ritchie flow is called Ritchie soliton if it moves only by a 1-parameter group of diffeomorphism and scaling. A Ritchie soliton on a Riemann manifold is generalization of Einstein matrix such that we have the condition that is 26. And we will use Lie derivative operator here along the vectors I on M. And of course, Ritchie soliton is said to be shrinking, steady, and expanding according to the lambda, that the behavior of the lambda. If it is negative, equal to 0, and positive, then we have shrinking, steady, and expanding respectively. For Riemann submersions, Merrick and Killick have studied Riemann submersion whose total manifolds admit a Ritchie soliton. And later on, the definition for the statistical manifold, it is given by
Alia. Sorry
yes.
to interrupt you. We are running late, so please.
I'm just okay, no problem. I'm just concluding. Okay,
Yeah,
no
okay.
Okay. So in our article, we have given the lemma below, which is for statistical submersion, and we have proved that the vertical distribution is parallel with respect to the connection nebula and nebula bar asterisk if the horizontal parts vanish identically. And with the help of this lemma, we have proved this theorem for the vertical distribution, which is parallel, and then we have omega is a statistical soliton, and which satisfies the equation number 28. And later on, we have such theorem, which is when your horizontal distribution is parallel, and we have two conditions. Sorry, we have two results for such condition. Next, inequalities on statistical submersion, which is the last topic of my talk, where we have studied three types of equations, inequalities. Chenrich inequality, which was given in 29, and it was studied by us in Chen inequalities for statistical submersion between statistical manifolds. And we have also proved under which conditions the equality case can be held. And we have also given the particular cases, that is Ricci bar and Ricci equal to 0. Then the Ricci inequalities is similar to that the Gulbar, as they have found for this in their paper, and the inequality for defined by Atomur and C. Osger in their paper between demand and submersions. We have put 30th equation in 29th, the main equation inequality. Again, we get inequality between delta and the mean curvature. Next, we have found delta 2 by 2 type inequality in the same paper. And we have used the lemma below, that is given by Mihai and Mihai. And this is the inequality which has been proved, including we obtained Colby from the main theorem. And last equation, last inequality was vertical Casaretti curvatures. Recently, we have proved this inequality for statistical submersion in our recent article, that is lower bounds on statistical submersions with vertical Casaretti curvatures. These are the main results, 43 and 44 inequalities. And these are the conditions from which we can say that these inequality can convert into equality. These are the consequences. Thank you. Thank you so much.
Thank you, Dr. Alia.
Thank you.
Any questions? Very precise. Any suggestions? So, okay. Thank you, Dr. Alia. So,
thank you.
In this session, I'm thankful to the participants, Dr. Danish, Dr. Mohin, Mobin, Dr. Ramshankar, Dr. Alia Naz, for sharing their contributions in the field of technical geometry. So thank you very much. Now, sir, Dr. Ramshankar Gupta ji, are you there?
Yes, yes, I'm here, sir.
Yeah. So now I hand over to you, sir.
Okay, thank you, sir. So next talk will be by Dr. Kamran Khan. His talk will be on sequential warp product submanifolds in nearly Kähler manifolds. Dr. Kamran Khan did his MPhil PhD from Aligarh Muslim University. He also qualified NET and JRF GATE. Now he is associated with Department of Applied Mathematics, Aligarh Muslim University. Now I invite Dr. Kamran Khan for his talk. Please, sir.
Thank you, sir. Just give me 1 minute.
Okay, please.
Okay, sir. Is my screen visible, sir?
Yes, yes, it is visible.
Okay, thank you, sir.
Yeah.
Okay, good afternoon, all of the participants. I'm going to present on sequential warp products of manifolds in nearly scalar manifolds. So, as sir have already told me about me that I am associated with the Department of Applied Mathematics, Aligarh Muslim University. Okay, so I will talk about sequential warp products of manifold, but first of all, I will brief some basic results about the warp product manifolds and some basic definitions. Actually, this sequential warp product manifolds is a class which is defined by S. Shenawi on in this paper on note on sequential warp products of manifold, and later UCD and S. Shenawi and B. Unal studied sequential warp products of manifolds in a detailed format. So in this article, before my article, B. Sahin studied sequential submanifold as warp product submanifolds in a scalar manifold. So motivated by those results, I have tried to obtain some results in sequential warp product submanifolds in nearly scalar manifolds. As we know that warp product manifolds have many applications in physics, relativity. So like basic solutions to Einstein field equations can be given by warp product manifolds. Also, Schwarzschild solution and Robertson-Walker model are also the warp product manifolds. Also, we know that modeling of a space-time near black holes can be done by the warp product manifold. So this is how the study on warp product manifold is very important. So in this paper, we studied only about the sequential warp products of manifolds. We obtained some inequalities like chains inequality in sequential warp products of manifolds and estimated the squared norm of the second fundamental form in terms of the warping function and Celan function. So before going to main results, I would just like to recall some basic definitions that we know that an almost Hermitian manifold is called nearly scalar manifold if the almost complex structure J is satisfies this condition that del bar u ju equal to 0, where u is any vector field on the manifold M bar and del bar is the connection. Also, we know that del bar u jv, that is the derivative of the J, is given by this equation del bar u jv minus J del bar u. Also, we know that the manifold will be scalar manifold if this almost complex J is parallel, that is its derivative is 0. Now, in this sequential warp products of manifold, we have used three types of distributions, or we can say that three types of submanifold. One is holomorphic submanifold, and that is totally submanifold, and the third is pointwise slant submanifold. So we know that a distribution D we denote by this dt. A distribution dt is called the holomorphic distribution if it is invariant with respect to J. That is, J of dt will be in dt. Also, a distribution is called the totally real distribution if action of the almost complex structure J on the distribution will give the vector fields in the normal bundle. Now, if we take the holomorphic distribution and totally real distribution, then it's ortho complementary distribution. Then a CR submanifold is defined as that it is we take if both the distribution then orthogonal complementary, then the submanifold is called the CR submanifold. Now we define slant submanifold or slant distribution. A distribution is called slant distribution if we take any point in the submanifold and we take any vector field in this distribution, and if it is independent of the angle, if it is independent of the choice of the point and the this vector field, then the submanifold or the distribution is called the slant distribution, and this angle theta is called the Wirtinger angle. Also, if we this distribution depends only on this vector field x, that is, it is also independent of the choice of the point, then the such distribution is called the pointwise slant distribution, and in this case theta is called the slant function. So we can say that a submanifold is actually the we can say that a slant submanifold is the more general to the holomorphic or totally real. That is, if the angle is 0, theta is 0, then the submanifold will be holomorphic, and if theta is pi by 2, then the submanifold will be totally real. Also, if the whole of the submanifold is we can take the submanifold as point-wise strand if the whole tangent bundle is point-wise strand. Also, the squared norm of the second fundamental form is defined like this. Now we come to the definition of the Waugh product manifold. A Waugh product manifold is actually the product manifold of the two submanifolds. We can take N1 and N2, and F is the warping function. So if this product manifold is accompanied with this metric, where Gn1 is the metric on the first manifold N1 and Gn2 is the metric on the second manifold N2, then the manifold is called the Waugh product manifold. Here F is the positive valued function, smooth function on the first manifold N1. This function is called the warping function, and if we take this function as constant function, then the Waugh product is a trivial. That is, it will be only the Riemannian product of the two submanifolds. Similarly, we can define multiply Waugh product manifolds. That is, if we take N1, N2, N3, and so on up to Nk submanifolds, and we take the product of these submanifolds, then we can define the multiply Waugh product submanifold as the product submanifold with this metric. Now, also in this case, all the functions are called the warping functions, and if all the functions are constant, then the Waugh product is trivial Waugh product. Now here we define sequential Waugh product. So if we take three submanifolds N1, N2, N3, and if we take a matrix G1, G2, G3 on these N1, N2, N3, if this function F is defined on N1, positive valued function defined on N1, and if the function H defined on N1 cross N2, then we can say that this type of product manifold N1 cross N2 cross N3, we can denote this by N1 cross F N2 cross H N3. So, and the metric is this G1, F square G2, and H square G3. So with this metric, this product manifold is called the sequential Waugh product manifold. So this sequential Waugh product manifold was defined by S. Shinawi and studied by UCD also. And in Kähler, this type of Waugh product manifold was studied by Sahin. So in this paper, we studied this Waugh product manifold in nearly Kähler manifold. Okay, so here, as we have seen that there are three submanifolds, N1, N2, N3. And here we are taking these submanifold as, we are taking one as holomorphic submanifold, second totally real submanifold, and the third as point-wise strand submanifold. So we can see that there are 6 possible sequential Waugh product submanifolds. As we can take NT cross Fn perp, then cross Hn theta, or we can take N perp cross Fnt cross Hn theta, and similarly. So there are 6 possible sequential Waugh product manifolds. So these all sequential Waugh product manifolds was studied by Sahin in his paper in Kähler manifold, and he has proved that the Waugh product from these 6 Waugh product manifold, the Waugh product manifold of the type second, third, fourth, fifth, and sixth, these Waugh product manifold do not exist in Kähler manifold. Only the first type of Waugh product manifold exists in Kähler manifold. He has also given the example for this first type of Waugh product manifold. So here it means we can say that if this first type of Waugh product manifold, sequential Waugh product manifold exists in Kähler manifold, so we can also study this Waugh product manifold in nearly Kähler. Okay. So in this paper, we studied this first type of Waugh product manifold in nearly Kähler, and we also talked about the other type of Waugh product manifolds. So we have used some previous results to show that actually we have proved this that if we take the sequential Waugh product of type this, that is N theta cross F N per cross H N T. So we have proved that this type of Waugh product manifold do not exist in nearly Kähler manifold. This type of sequential Waugh product manifold do not exist in nearly Kähler manifolds. Now, for the rest type of Waugh product manifold, first we use a theorem which is proved by V.A. Khan, that if we take the Waugh product manifold of type N cross psi NT, where N is any Riemannian submanifold and NT is holomorphic submanifold. So V.A. Khan proved that this type of they call this type of Waugh product manifold as generic Waugh product manifold. So they proved that this type of Waugh product manifold do not exist in nearly Kähler manifold. So by using this result, we can say that if we take NT as the last term, then we can say that our Waugh product manifold of second and fourth type, the second type and fourth type, that is here we are taking n perp cross f nt, and here we are taking n theta cross f n perp. So these type of product manifold also, we cannot actually
Dr.
study this
Kamran,
type of sequential
excuse me.
product manifold in early case. Yes, sir. Yes, sir.
We
Yes,
have very
sir.
limited time, so please wind up in 2 minutes, please, if possible. Okay, thank you.
Yeah, okay, sir. Okay, so I have already told that we are studying only the first type of sequential VAR product manifold in this paper. So I am going to show that the results. We have found the inequalities like chains inequalities. So if we have this type of sequential VAR product manifold, so we can take the dimension of m as some n, and we can take the dimension of nt as even dimension p, which is equal to 2m, and so on. Okay, so we proved that if we take the sequential VAR product manifold of this type, nt cross f1 cross h and theta, where p plus p, the dimension of this will be p plus q plus r, then we have found this inequality for the squared norm of the second fundamental form. And here actually the n theta is the point-wise trend. So we have also got the some terms in terms of theta also. And we have also studied some special condition that if we can take the inequality here, then nt cross f n perp is totally geodesic and n theta will be totally umbilical with some conditions actually. Also, so if we take dimension of n perp equal to 0 here, so if we take dimension of n perp equal to 0, so then the sum manifold will be point-wise semi-slant sum manifold. And in this case, we will get this result. So this result was also proved earlier. So our from our result, we can derive this result for the point-wise semi-slant sum manifold in nearly scalar manifold. Also, actually, I have some more results, but in PDF, but due to the shortage of time, if I have time, then I can show, sir. If I have 1 minute.
Okay, just finish. Yeah, please.
Okay. So I have some more results in PDF format. Actually, I didn't get time to include in the presentation. That for semi-slant VAR products of manifold, we have this result. In this case, we have taken dimension of n perp equal to 0, and also these results coincide with the earlier proved results. And also for this, if we take dimension of n theta equal to 0, then our submanifold will be CR VAR product submanifold. So in this case, we get this inequality, and this inequality was proved by chain. In case norm of sigma, it is proved by chain in scalar manifold, and it is proved by VA Khan in nearly scalar manifold. Okay, so thank you, sir. I am just going to show the references.
Okay, thank you. Is there any question, any queries? If not, just one thing I want to know,
Yes,
Dr. Kamran.
Yes,
is the VAR product function always has to be positive?
Yes, sir. It is a positive valued function.
Why? What is the reason?
Sir, actually, VAR product is defined for the positive valued functions.
Okay. Okay. It's okay. Thank you so much. Thank you. It's an interesting talk. Thank you.
Thank you, sir.
Now, our next speaker is Dr. Sushil Shukla. He will present his talk on light-like hypersurface of indefinite Vacant space for. He did his UG and PG and PhD from University of Allahabad.
Yes, sir, I am present here. Yes, sir, I am present here.
Okay, yeah, we can hear.
Yes, sir.
Yeah. And he is associated with Purvanchal University, Department of Mathematics. So now you may start, please. Dr. Sushil Shukla.
Sir, I am sharing my.
Yeah, please share. Yeah. So please take care of time. You may finish your talk between 10 to 15 minutes. That will be good enough for us. Yeah, Dr. Susil, are you sharing your work?
Yes, sir. Copying.
Hello.
Yes, yes.
Yeah, nothing is visible, sir.
Yeah,
Sir,
yeah.
I am trying. Please submit.
Trying, yeah.
Sir, is it visible?
Yeah, now it is visible.
Respected chairman of the session and participants, first of all, I am thankful to the organizers for providing me opportunity to present the paper. The topic of my paper is on light-like hypersurfaces of indefinite Sasakian space form. And the object of present paper is to study the properties of light-like hypersurfaces of indefinite Sasakian space form with a LM type connection. Before giving the details, I want to here describe some basics. A linear connection delta bar on a semi-Riemannian manifold M bar G bar is called a LM type connection, which is given by Jin. If delta bar and its torsion tensor T satisfies delta bar x bar G bar y bar Z bar equal to L times theta y bar G bar x bar Z bar plus theta Z bar G bar x bar y bar minus m theta y bar G bar J x bar Z bar plus theta Z bar G bar J x bar y bar, and torsion tensor T bar x bar y bar equal to L theta y x bar minus theta x bar y plus m theta y bar J x bar minus theta x bar J y bar, where L and M are two smooth functions on M bar and J is a tensor field of type 1, and theta is a one form associated with a smooth unit vector field J, which is called the characteristic vector field of M bar, given by theta x bar equal to G bar x bar J bar. By direct calculation, it can easily seen that a linear connection delta bar on M is a LM type connection if and only if delta bar satisfies delta x bar y bar equal to delta x bar y bar plus theta y bar Lx bar plus mjx bar, where L is the Levi-Civita connection of a semi-Riemannian manifold M bar G bar with respect to G bar. Actually, this LM type connection is the generalization of different type of connections taking different values of L and M. For example, if we take L equal to M and M equal to 0, the above connection becomes a semi-symmetric non-metric connection. And the notion of semi-symmetric non-metric connection on a Riemannian manifold was introduced by Agassiz and Chapley, and later studied by several authors. And if we take L equal to 0 and M equal to 1, the above connection becomes a non-metric phi symmetric connection such that phi x bar y bar equal to G J x bar y bar. The notion of non-metric phi symmetric connection was introduced by Jin. And if in case if we take L equal to 1 and M equal to 0 in first equation and L equal to 0 and M equal to 1 in second equation, then this connection becomes a quarter symmetric non-metric connection. And the notion of quarter symmetric non-metric connection was introduced by Golab and studied by Sen, Gupta and Vishwas. And in case we take both LM 0 in first equation and L equal to 0 and M equal to 1 in the second equation, then the above connection becomes a quarter symmetric metric connection. And the notion of quarter symmetric metric connection was introduced by Yano and Imai. In case L equal to 0, M equal to 0 in first equation and L equal to 1 and M equal to 0 in second equation, this connection becomes a semi-symmetric metric connection, and the notion of semi-symmetric metric connection was introduced by Haydn. The light-light geometry has been studied by K.L. Duggal and A. Vejaku, and later by D.N. Kupeli with different approaches. Recently, many geometers investigated light-like hypersurfaces by using the fundamental knowledge introduced by Duggal and Vejaku with various geometric conditions and obtained many important results. For example, D.H. Jin proved a classification theorem of light-like hypersurfaces with totally umbilical screen distribution of a semi-Riemannian space form. C. K.L. Duggal introduced screen conformal light-like hypersurface and proved that its induced Ricci curvature tensor is symmetric. Two monographs by Duggal and Jin and Duggal and Sahin contains a collection of many interesting results on light-like hypersurfaces and have further motivated other scholars to take an active role in the study of light-like geometry. References are given. Here I want to define what is Sasakian space form. On an indefinite Sasakian manifold M bar is called indefinite Sasakian space form if this condition is satisfied. Indefinite Sasakian space form are indefinite almost contact manifold with constant theta sectional curvature. This definition is also valid for a semi-Riemannian manifold. In the paper, Chin proved that let M be a screen conformal light-like hypersurface of an indefinite generalized Sasakian space form M bar F1, F2, F3, then F1, F2, F3 equal to 0. And in second paper, Chin proved that let F be a screen conformal light-like hypersurface of an indefinite nearly generalized Sasakian space form M bar F1, F2, F3 such that Xi is tangent to M, then F1, F2, F3 equal to 0. From
try to finish in 5 minutes.
Sir?
Please try to finish in 5 more minutes, okay?
Yes, sir. Okay. The object of present paper is to generalize these results for any LM type connection. Here, some basic definitions are this almost contact manifold. These are some basics which I used to prove my main theorem. These are the relations and calculations. These are calculations, relations on light-like hypersurfaces, and on some calculation on LM type connection. There is one proposition. Let M be a light-like hypersurface of indefinite Sasakian manifold M bar with an LM type connection such that Xi is tangent to M. Then V is symmetric if and only if M equal to 0. And this is its proof, and several relations developed to prove the theorem. These are the relations. Conformal spin distribution. Linear connection delta on M is an LM type connection if and only if delta satisfies this. These are the curvatures Gauss-Weingarten formulas. This is the definition of indefinite Sasakian space form. And here, one more definition: a light-like hypersurface M is said to be stream conformal if there exists a non-vanishing smooth function phi on M such that Cxpy equal to phi Bxpy. And the main theorem of the paper is this: let M be a light-like hypersurface of indefinite Sasakian space form M bar C with an LM type connection such that Chi is tangent to M. Then if M is screen conformal, then C equal to 1. And proof of this theorem is like this. By previous calculations, we proved this. And here are some references. Thank you.
Yeah, thank you, Dr. Susu. Is there any comments, questions, queries?
Yeah, please. First of all, I would like, please, may I can ask?
Yeah, please, you can ask.
Yeah, I would like to thank Professor Han about his talk, but I was surprised that talking about undefined Sasakian and for his main theorem, at least he must give him an example about the different distributions that he talked about. And also such hypersurfaces and define or light-like in with that conditions to see how it is going. This is one. Second thing is, for undefined is you have only almost three. For example, if we take Sasakian undefined, can you give us a little bit something very special for that? Heisenberg, I mean, we can say with holomorphic sectional curvature is -3 or +3 according. Is it defined or undefined? Okay, this is the question for Mr. Dr. Khan.
Dr. Susil, you may answer.
I think Dr. Sushil has already left.
Oh, okay. Okay, so then we move to our next speaker. Our next speaker is Inan Anand. His talk will be on some semi-symmetric condition on Kähler manifold. He did his PhD from Gazi University, PG from Firat University, and UG from Ankara University. Now he is associated with Department of Computer Engineering, Munji University, Turkey. So I request now Dr. Inan Anand, please present the talk.
Hello. Could you hear me?
Yes, we can hear.
Thank you very much. I think my presentation is visible.
Yes, it is visible.
Is it okay?
Yeah, visible.
Okay.
You can see.
Okay. Okay. Thank you very much thank you very much to organizer for this nice organization. I am very happy to be here with a presentation. In this talk, I want to mention some symmetric conditions on Kähler manifolds, which are related to H curvature tensors. As we know, a Kähler manifold is a very special kind of complex manifold, and also this type of manifold is very important in complex geometry. When we study on any subject or any subtitle for complex geometry, firstly we think Taylor manifolds, and first we wonder how we can see any effect of this new subtitle on these Taylor manifolds. So in this talk, my aim to give maybe a new perspective for semi-symmetric conditions on Taylor manifolds. A Riemannian metric on a complex manifold is called Hermitian if it is compatible with the complex structure of this manifold. We know an Hermitian metric have this property. Also, we have an associated differential 2 form, which is defined by this equality, and this form is called by Taylor form. It turns out that omega is closed if and only if G is parallel. Then M is called a Taylor manifold, and the metric on M is a Taylor metric. Taylor manifolds are modeled on complex Euclidean space. The main example of complex example is complex projective space endowed with the Fubini study metric. Because we talk about curvature properties, let's remember some fundamental facts from Riemannian geometry. First one is Riemannian curvature. Riemannian curvature Taylor manifold is defined by this equality, and also we state this for tuple equality. The Ricci operator is given by the trace of Riemannian curvature tensor, and Ricci curvature is equal to this equation, and scalar curvature is also trace of Ricci curvature. They are well-known formulas. The important properties of Taylor manifolds are comes from curvature properties, which we use in this study. On Taylor manifolds, we have following curvature equalities. The first one is the first two of them is about invariance under G, and the third is also about Ricci curvature related to complex structure, and the third is about Ricci tensor. And finally, in fifth, we have maybe you can say antisymmetric properties of Ricci tensor related to complex structure. Except for Riemannian curvature tensor, we well know we have some other important tensors which have similar properties with R. Many of these curvature tensors are projective, conformal, concircular, quasi-conformal, conharmonic, and some of others. The curvature tensors on Taylor manifolds were studied by Sinha by a different name, is called by H tensor. H tensors comes from the curvature properties of any Taylor manifold. So Sinha defined H projective, H conformal, H concircular, and H conharmonic curvature tensor. Also, in this paper, in some of our paper with my supervisor, we give a definition for H quasi-conformal curvature tensor, and we use these curvature tensors for İK normal, İşara Konishi normal complex contact metric manifolds. H projective curvature tensor for n plus 2-dimensional Taylor manifolds defined by this equation, and H conformal curvature tensor is defined by this equation. For H concircular and H conharmonic, we have following equations. And finally, for H quasi-conformal curvature tensor, we have this form. In here, we mentioned before, Q is Ricci operator, G is complex structure. Symmetry also is very important notion. It mentioned some of other talks by many important different researchers. Thank you very much to them. So I want to recall some basic facts from Riemannian geometry. This product acts like a derivative operation. And if R dot R equal to 0, we say that manifold is locally symmetric. For any curvature tensor, if R dot equal to 0, then the manifold is called T-semisymmetric manifold. Also, for any 1-1 type tensor, we have this equality. And for Ricci curvature tensor, also for any 0-2 type tensor, we have this equation. Okay, we consider H curvature tensors for these different symmetry conditions, and we wonder how these conditions affect to Taylor manifold. Firstly, we think the H projective curvature tensor, and we take T by H projective curvature tensor, and by using curvature properties of, by using curvature properties of Taylor manifolds, after a long computation, we obtain our first theorem. This theorem states that a Taylor manifold is H projectively semisymmetric if and only if it is locally symmetric and R dot Q equal to 0. And secondly, we think the Taylor-Einstein manifold, which is a Taylor manifold satisfying Einstein-Field equations. Also, we can say that Ricci tensor is equal to a constant multiple of metric tensor. When we think this structure, we obtain following corollary. A Taylor-Einstein manifold is H projectively semisymmetric if and only if it is locally semisymmetric. So we can say that H projectively semisymmetric reduced to locally semisymmetric for in this case. Secondly, we think the H conformal curvature tensors, and we by following same steps before calculations, and after also thinking the definition of conharmonic curvature tensor and curvature properties of Taylor manifolds, we get following theorem. A Taylor manifold is H conharmonically semisymmetric if and only if it is locally semisymmetric and R dot Q equal to 0. I'm sorry, I forgot to write it here, equal to 0. Then for H quasi-conformal curvature tensor, after following same process and consider the definition of H quasi-conformal curvature tensor and curvature properties of Taylor manifolds, we obtain a Taylor manifold is H quasi-conformally semisymmetric if and only if it is locally semisymmetric and R dot Q equal to 0. We know Ricci semisymmetry is a generalization of Ricci symmetry. An Einstein manifold is Ricci semisymmetric, but the converse it is not true in general. In fact, the authors studied on Ricci semisymmetric complex contact manifolds. So we think let's take H projective curvature tensor for T, and by following similar calculations, thinking the symmetry properties and definition, we obtain that a Taylor manifold is H projectively semisymmetric if and only if it is Ricci semisymmetric. Similarly, for H conharmonic curvature tensor, we see that a Taylor manifold is a Taylor manifold M is H conharmonic, which is semisymmetric if and only if it is Ricci semisymmetric and also satisfy this condition, this equality. On the other hand, for quasi-conformal curvature tensor, by using same approach, we obtain the following theorem. A Taylor manifold M is H quasi-conformal Ricci semisymmetric if and only if it is Ricci semisymmetric and Q square equal to identity map. By using the definition of H projective curvature tensor and by using the definition and curvature properties of Taylor manifolds again and again, we see that in a Taylor manifold M, if this condition is satisfied, then the scalar curvature is equal to 4n. The dimension of manifold 4n plus 2. So we can say that scalar curvature is dimension minus 2. If the manifold is Einstein, then we get cosmology constant lambda by this. By following same steps and using definition of H curvature tensor, we obtain following result. In a Taylor manifold M, if we have this equality, this means H conharmonic curvature tensor and dot G equal to 0, then Ricci curvature has this form. And suppose that H quasi-conformal dot G equal to 0 and take inner product with any vector file X4. In addition, choose X2 and X3 by the orthonormal vector files. We obtain following result, and then we can state this theorem in a Taylor manifold. If we have this condition, then the Ricci curvature of manifold has following relation. I'm sorry. Here are my references. Thank you very much.
Is there any question, suggestions, feedback?
I have some remarks,
Okay,
possible,
please.
for my friend
Yeah.
Onan.
Please.
First of all, I would like to thank you very much, Onal, for your nice talk. Just please, can you show me about complex contact, such conditions that you give them related to this for complex contact? Just I have some comments. Please try to give me the slides.
Okay.
The right slide about complex, just to.
I did not mention conditions on complex contact manifolds. But
Just to show that for quickly.
Okay.
So, to see.
Okay.
Yeah, more or less. I mean, all the conditions are. I mean, also all locally symmetric. I mean, all conditions. So it gives give you. We can say locally symmetric.
Yes.
And R dot Q is 0. So.
Yes.
So
Yes.
for this and for this is for investigation. So just try to give me the about complex contact. That R dot Q is 0. So can you give? Yeah.
For complex contact.
Pardon me. Just for we have here. This is a characterized actual project of semi if on if. Yeah, it's locally symmetric and R dot Q 0. Yeah. So for R dot Q, do you have any investigation about R dot Q 0? Just only like that. And
Yeah.
This is first question. Second question, just to try to show me complex contact. Just I think I have remarked just about this. Just you give something about complex contact.
Okay, dear Professor, thank you very much. In here, I think you know that we separate the complex contact manifolds into two, maybe we can say two subfiles or subclass. The first one is Ishara-Konishi normal complex contact manifolds, and the second is Korkmaz normal complex contact manifold. We know that the Korkmaz normal complex contact manifold is not Taylor. So these conditions do not work on this structure. But now I am working on for Ishara-Konishi normal complex contact manifold, and I will add a new section to this study for IK normal, Ishara-Konishi normal complex contact manifold. I'm not sure I can answer your question or not.
No, but anyway, it's okay. It's okay. I know your work. I mean, very well. It's just to And do you have, for example, an example of Carl Einstein?
Okay. Also, EK normal structure is a good example for Taylor-Einstein manifold. So I think these conditions will work on this structure.
Okay, thank you very much.
Thank you very much. I'm
Thank
sorry if I cannot answer your question. I'm sorry.
No, it's okay. It's okay. It's okay. No, we will have. I mean, I will send you an email about that.
Thank you very much.
Thank you very much. It's nice. Thanks.
Yeah. Now, Professor Sheikh, you may ask your question, please.
Yeah, I will not like to ask the question, but I have some suggestions.
Yeah, please.
You have considered various kinds of curvature curvature tensors. Okay.
Yes.
So some of them are generalized, some of them are not. Especially for the projective case, it is not generalized curvature tensor.
Yes.
I think all the theorems from 2.1 is a series of theorems by considering the different curvature tensor can easily be stated with a single theorem by considering the generalized curvature tensor. Okay, and there are many semisymmetry conditions are equivalent to each other with different curvature tensors. Okay.
Yes.
And that has been shown by me in a paper published from Journal of Geometry.
Yes.
Maybe in 2014 or 15 with my student H. Kundu. You can see there some of the semisymmetry conditions are equivalent.
Yes,
Those
I know your paper.
Yeah. So
yeah, I know. I read.
Yeah. So you should go through that paper and you combine all these results by a single result for generalized curvature tensor and which are not generalized curvature. Then it will be very nice. Okay.
Okay, dear professor. But in here we have I think we have an obstacle or a question. Because H curvature tensor comes from the curvature properties of Taylor manifolds, so we must study to define generalization of these tensors. This is also an open question for me, but I could not deal with this problem in the past. But for future, I think this your advice. Thank you very much.
No, it's okay. You have studied in a Kyler setup. That's okay. But my suggestion is you consider the generalized cases. So some of the curvature tensor will combine, and those who are not generalized. Okay.
Okay.
So not necessary to treat every curvature tensor separately. Okay.
Yes.
This is my suggestion.
Yeah.
You
sorry,
follow
just
my
remark.
paper
But the problem is when is, for example, is looking for generalization. Yeah, he should have. I mean, at least one motivation or two, because I know his way what is working. So there is no meaning of to generalize any curvature. You should give a motivation about that. Yeah. Thanks.
Yeah. Of course.
Yes, the generalization of curvature tensors also is sometimes problem in generally.
Because all these curvature tensors that appears through the different kinds of transformations. Okay.
Yeah.
So that's why Professor Mohammed is saying you should give this motivations behind this H projective curvature tensors.
Okay.
Okay, maybe you can see this paper, some Indian fellow who is in abroad, GP Pokharial. Recently, he has with some of these applications in electromagnetic field theory like that. You can see there, you can have the motivation also there.
Yes, thank you. I know his papers, significations of curvature tensors, some different kind. I know.
Okay, thank you.
Thank you very much.
Is there any other suggestions, comments? If no. Okay, thank you. Thank you, Dr. Inanunal. Thank you so much for your interesting talk. So now I would like to thank
you very much again.
Yeah. Now I'd like to thank the speaker about this session and the participants for useful discussions. Now I hand over this to Majid. Majid bhai, please.
Thank you very much, sir. And, I must be thankful to Dr. Subhash Ala and Dr. Ramshankar Gupta for accepting our invitation to chair these two sessions. I'm also thankful to all the participants who delivered their talk, especially Dr. Danish Siddiqui, Dr. Nubeen Ahmed, Dr. Ramshankar Gupta, Dr. Alia, Dr. Kamran, Dr. Sushil Shukla, and Dr. Inamina. Actually, all presented very well, and all the lectures very beautiful. And more interesting thing is the presence of eminent speakers like Professor of Sociology, Dr. Professor Mohammad Bal Khalifa made it more beautiful and more encouraging to Jumaters like us who can learn more things. So we hope same type of things tomorrow, inshallah. So I thank one and all who contributed anyway in making this day wonderful. Thanks once again. Thank you, Dr. Mohammad Bal Khalifa and Dr. Afsoos Ali Sheikh, sir. Very much thankful to you, sir.
Okay, thank you.
Thank you very much.
You also. Thank you, Dr. Majid.
Thank you
for organizing such type of nice conference. It is really very academic conference because in most of the conferences people are coming and these papers almost reading there is nothing. Almost nothing, but it is truly academic conference because the papers and the lectures which I have heard, it's very interesting to me also. So thank you. See you tomorrow. Thank you again, the organizers, for organizing such wonderful and interesting conference. Thank you very much. So with your permission, I am leaving now.
No, sir, I'm not here to give you permission, sir.
Okay, thank you. See you tomorrow.
Okay, sir. Okay, sir.
Bye. Assalamu alaikum.
Najam, sir. Najam, sir.
Yeah, Chief. Thanks a lot. Yeah, please. Yeah, it was a wonderful session. All the sessions were very good. Congratulations and looking forward for tomorrow's sessions.
Thank you,
Well,
everyone. Thank you. Goodbye.
Assalamu
Assalamu alaikum.
Assalamu alaikum.